Almost 2,500 years ago in ancient Greece, the philosopher Leucippus and his student Democritus reasoned that if a sample of solid matter, such as gold, was repeatedly cut into smaller and smaller pieces, the eventual result would be a particle so small it couldn't be cut into anything smaller. Democritus called these smallest particles of matter atomos, which is Greek for uncuttable. The ancient philosophers relied largely on intuition rather than experimentation for knowledge, and soon this idea was replaced by Aristotle's theory that all matter consisted of varying proportions of four elements: earth, air, fire, and water. During the late 1600s, the scientific revolution saw the emergence of Robert Boyle, who is regarded as the first real scientist. Boyle was the first person to perform and publish the results of true quantitative experiments, and his observations convinced him that the four-element idea proposed by Aristotle was incorrect. As Boyle's insistence on experimentation gained acceptance, more and more elements were discovered, and Aristotle's ideas about matter were eventually discarded. Further studies over the next 140 years by such scientists as Carl Scheele, Joseph Priestley, Anton Lavoisier, and Joseph Proust resulted in mass laws governing compound composition and chemical reactions. It was these laws that were used by English schoolteacher John Dalton in 1808 to present a theory about matter first suggested more than 2,200 years earlier. The main points of the theory are as follows. All matter is composed of extremely small particles called atoms, which cannot be broken into smaller particles, created or destroyed. While groundbreaking, this is not exactly correct. For instance, we will talk soon about smaller particles which make up atoms. The atoms of any given element are all identical to each other and different from the atoms of other elements. This is also not entirely accurate, but we'll get to that later when we talk about isotopes. Atoms of different elements combine in specific ratios to form compounds. This relates to the law of multiple proportions, which states that if two elements form more than one compound, then the ratios of the masses of the second element, which combine with a fixed mass of the first element, will always be ratios of small whole numbers. This law is also known as Dalton's law. Finally, in a chemical reaction, atoms are separated, rearranged, and recombined to form new compounds. While Dalton's theory was a major step forward in our understanding of matter, even more captivating discoveries about the atom were just around the corner. One of which resulted from work done by Julius Plucker in Germany and William Crookes in England. One device that Crookes worked with consisted of a sealed glass tube connected to a vacuum pump. The tube contained a negatively charged electrical terminal, a positive terminal, and a broad, flat cross. When a high voltage was applied across the electrodes as the air was being pumped out, any air remaining in the tube began to glow. As the air was removed, the glow faded, but a shadow of the cross surrounded by a faint green glow could still be seen at the end of the tube opposite the cathode, as well as a very faint glow coming from the cathode itself. This led Crookes to conclude that something must be traveling from the cathode to the other end of the tube, even though all the air was gone. In Paris, Jean-Baptiste Perrin discovered that a magnet placed next to the tube was able to deflect the mysterious beam, and concluded that the mysterious cathode ray must be a stream of charged particles. In 1897, English physicist J.J. Thomson set to work to discover the nature of the cathode rays. He modified the original Crookes tube by passing the diffuse cathode ray through a small hole drilled in the center of an anode and directed that narrow ray onto a fluorescent target. Between the anode and the target, he placed an electric field. When the focused cathode ray was deflected towards the positive plate, Thomson concluded that the charge on these moving particles must be negative. He knew that the amount of deflection a charged particle experiences in an electric field depends on the ratio of the particle's charge to its mass, and was able to calculate this ratio for the negative particles composing cathode rays. He found that value to be 1,840 times greater than the charge-to-mass ratio for the hydrogen ion, which was the smallest particle known in 1897. Thomson concluded that the magnitude of the charge on these negative particles must equal that of hydrogen ions, but that the mass of the particles was actually 1,840 times less than hydrogen ions. Thomson repeated the experiments many times with different metals used as the cathode and even different gases inside the tube, but the results were always the same. This had to mean that these mysterious negative particles were present in atoms of different elements. In a speech given to the Royal Institution in 1897, J.J. Thomson told his audience that cathode rays were actually tiny, negatively charged corpuscles of electricity, later identified as electrons. He also reasoned that if an intact atom has no charge, then there must be something positive in an atom to balance the negative charge on the electron. German physicist Eugen Goldstein had also conducted experiments in the late 1800s involving cathode ray tubes. He observed rays traveling in the opposite direction to cathode rays, which were composed of positively charged ions whose identity depended on the residual gas in the tube. His work with rays of hydrogen ions was likely the first observation of protons, but their nature was not fully understood at that time. In 1903, Thomson suggested that an atom could be seen as a spongy ball or plum pudding, with negative electrons distributed evenly throughout a positively charged, spongy mass. Ultimately, the two most important components of Thomson's atomic theory were that atoms are built from smaller components and that these components are oppositely charged. In 1895, young Ernest Rutherford received a scholarship to study at the University of Cambridge under J.J. Thomson's guidance. He arrived in time to work with Thomson during the discovery of the electron and, not surprisingly, fully believed in the plum pudding model of the atom. He also conducted research exploring radioactivity and using samples of radioactive elements, such as radium provided by Marie and Pierre Curie. He and Frederick Soddy discovered 3 types of emissions associated with radioactivity. They labeled these emissions as alpha particles, beta particles, and gamma rays. Out of the 3, gamma rays are the fastest and have the greatest penetrating ability, while alpha particles are the slowest and have the least penetrating ability. In 1911, working with colleagues Hans Geiger and Ernest Marsden, Rutherford used alpha particles as a type of probe to test the makeup of the atom. The experiment involved aiming alpha particles emitted from a radioactive source at very thin sheets of gold foil. He fully expected that nothing in Thomson's spongy atom was capable of significantly altering the path of alpha particles traveling at 16,000 kilometers per second. The vast majority of alpha particles behaved exactly as predicted, but a few particles deviated through large angles. A very few didn't go through the foil at all and instead bounced back. Thus, nothing in Thomson's atomic model was capable of knocking an alpha particle far off its course. It clearly needed a major revision. Rutherford explained the results by suggesting that virtually all the mass of an atom was concentrated in a very tiny, dense, positive structure at the atom's center, he called the nucleus, which was surrounded by a cloud of negatively charged electrons. Note that it would make sense for the nucleus to be positively charged since alpha particles, which were deflected, are positively charged. Although his model for the atom resembled a tiny planetary system with electrons orbiting a nucleus much like planets orbit the sun, he warned that the analogy should not be pressed too far. While his model explained the charged nature of the atom, Rutherford realized it couldn't account for all of its mass. He believed that a neutral particle must also exist in the nucleus that added mass but no charge to the atom. This particle, the neutron, was discovered more than 20 years later by British physicist James Chadwick. Here is a simplified summary of the composition of the atom as we view it today. Note that although the neutron is slightly heavier, its mass is almost identical to that of the proton. We'll now move on from our discussion about the models of the atom and take a look at 3 important numbers associated with every element. The atomic number, Z, of an element equals the number of protons in the positive charge on the nucleus of each of its atoms. All of the atoms of a given element have the same atomic number, and each element's atomic number is different from that of any other element. For example, there are 6 protons in the nucleus of every carbon atom. The key point here is that it is the number of protons that determines the identity of an atom. The mass number, A, for each atom equals the sum of the number of protons and neutrons in the nucleus. Note that while the number of protons always remains the same in atoms of the same element, the number of neutrons may vary. The neutron number, N, can be calculated by subtracting the atomic number from the mass number. For example, an atom of aluminum with a mass of 27 and 13 protons has 14 neutrons. Any particular atom can be represented using nuclear notation, which includes the element's symbol, mass number, and atomic number. For example, we can see that this represents a uranium atom with 92 protons, a mass number of 235, and 143 neutrons, which would be read as uranium-235. We can use the same notation to represent ions, such as a nickel cation with 28 protons, 30 neutrons, and 26 electrons. As a quick exercise, determine the number of protons, neutrons, and electrons in the following. You can just pause the video and calculate this in your head if you want. Okay, here are the answers. We'll just take a look at the process for the silver cation since it's pretty much the same for each of these. We know from the atomic number 47 that there are 47 protons. Subtracting the number of protons from the mass number yields the number of neutrons. If this were neutral silver, then we'd have the same number of electrons and protons. But since it's an ion with a charge of +1, one electron must have been lost, so we have 47 minus 1, or 46 electrons. Isotopes are different forms of the same element with different numbers of neutrons, and as a consequence have different mass values. The number of naturally occurring isotopes of an element and their relative masses and abundances may be determined by a mass spectrometer, an instrument based on the same principles employed by J.J. Thomson to discover the electron. Mass spectrometry uses the fact that charged particles moving through a magnetic field are deflected from their original path based on their charge-to-mass ratio. Consider the example of a beam of ionized neon containing the isotopes neon-20, neon-21, and neon-22. The beam enters the magnetic field chamber and then the three isotopes separate on the basis of their charge-to-mass ratios. Neon-20 would be deflected the most since all these isotopes have the same charge +1, but neon-20 has the smallest mass and thus the largest charge-to-mass ratio. The mass number for neon that appears on the periodic table is the weighted average of those naturally occurring isotopes. We'll go through two examples relating to mass spectrometry. The first one requires using data to calculate the mass of gallium. There are two isotopes and we're given the mass and percent abundance in nature of each. We can determine the mass of gallium by calculating the weighted average of the masses of each isotope. In other words, we simply take the sum of the isotope masses multiplied by the isotope's percent abundance, though we want to express the abundance as a fractional abundance. To convert from percentage, we simply divide by 100. We only round at the very end, making sure the number of decimal places matches the precision in the given percentages. In this next example, we're given the atomic mass of chlorine and the isotopic masses of its two naturally occurring isotopes, so that we can determine the percent abundances. Now, we could set up an equation in the same form as the previous problem, but we have two unknowns here, the percent abundances. However, if these are the only two isotopes, then the percent abundances have to sum to 100%. Or, said differently, the fractional abundances have to sum to 1. If we let the fractional abundance of chlorine-35 be x, then the fractional abundance of chlorine-37 would be 1 minus x. Now we can write our weighted average equation down and solve for the one unknown, x. We do some algebraic manipulations to isolate x, and can quickly determine the value of 1 minus x. Converting to percent abundances by multiplying by 100, we get our final answer. In this next section, we will explore the quantum mechanical model of the atom and how it describes electrons within the atoms of elements. We'll start with hydrogen and then expand our understanding to multi-electron atoms. While a comprehensive discussion of the quantum mechanical view is presented in sections 5.2 and 5.3, we'll briefly summarize three essential aspects. First, the energies of electrons and atoms are quantized due to their wave nature, meaning only certain allowed energy states associated with standing electron waves are possible. Second, the Heisenberg uncertainty principle states that we cannot precisely know both the position and momentum of an electron at the same time. Finally, atomic orbitals represent regions in 3D space around the nucleus where electrons with specific energy levels are most likely to be found. The analogy of a guitar string is often used to help explain the requirement of standing waves for the allowed energy states of electrons and atoms, but the three-dimensional electron waves or orbitals in atoms are more complicated than this. To describe them, quantum mechanics employs the use of special numbers called quantum numbers. Each quantum number specifies something different about the orbitals and electrons. The first quantum number is called the principal quantum number and is denoted by the letter n. It indicates the relative size of the atomic orbital, the number of orbital shapes or sublevels existing at that energy level, and also represents the allowed energy states for the electron. N is always a positive integer, for instance 1, 2, 3, and so on. When hydrogen's electron is in the lowest allowed energy state or ground state, then the principal quantum number is 1. Schrodinger's equation shows us where an electron possessing that amount of energy will most likely be found. There are a couple of ways we can visualize this, one being an electron probability density diagram resembling a spherical cloud, with the hydrogen nucleus at the center. If you could take many snapshots of the hydrogen electron around the nucleus and then superimpose all of them, it may look something like this. Ultimately, the cloud's density is greater near the nucleus and decreases as we move away, which tells us that the probability of locating the electron is higher closer to the nucleus and lower farther away from the nucleus. As we move out from the nucleus, we find hydrogen's electron in its ground state is likely to spend most of its time a slight distance from the nucleus rather than at the nucleus itself. This is called the radial probability. When we enclose the cloud in a volume representing about a 90% probability of finding the electron, we call this the 1s orbital. The number 1 represents the principal quantum number, and the letter s refers to the type or shape of the orbital. The assignment of all 4 quantum numbers is not required on the AP exam, but we'll quickly touch on what the other 3 numbers are. However, the principal quantum number should be our main focus and takeaway. The second quantum number is called the angular momentum quantum number. It relates the shape of an atomic orbital and takes on whole number values, so 0, 1, 2, 3, and so on. The third quantum number is called the magnetic quantum number and tells us the orientation in space of a given atomic orbital. This will make more sense once we look at some orbitals. The fourth quantum number is called the spin quantum number. It has 2 possible values, +0.5 or -0.5, which are the 2 possible electron spins. As for what is meant by electron spin, it is an intrinsic form of angular momentum. Experiments have shown that the single electron in hydrogen generates a tiny magnetic field, as if the electron were a spinning charge. While the earliest models for electron spin imagined a rotating charged mass, it should not be understood this way. While we don't dive into the intricacies here, it's important to understand that it's as fundamental a part of an electron's nature as its charge. Now that we've touched on the quantum numbers, let's get a better sense of what we actually mean when referring to the size, shape, and orientation of atomic orbitals. Each new energy level has one new orbital shape in addition to those existing in the previous level. So if hydrogen's electron is excited and absorbs enough energy to reach the second allowed energy state, then the principal quantum number is 2, and 2 orbital shapes or sublevels exist. There's a 2s orbital which has a shape identical to the 1s except it's larger, since the electron with this greater amount of energy will spend more of its time farther from the nucleus. While there was only one orientation for the s orbital, the p sublevel includes 3 separate orbitals, each with a different spatial orientation. If hydrogen's electron absorbs enough energy to reach the third allowed energy state, then in addition to one spherical 3s orbital and 3 dumbbell-shaped 3p orbitals, we also discover a third sublevel whose orbitals have a more complicated shape. This is called the 3d sublevel, and it contains 5 different orbitals. Though you may not be required to remember either their shapes or their names, you should know that there are 5 of them. In the 4th energy level, we see a 4th shape called the 4f sublevel. To quickly summarize what we've learned about energy levels and orbitals then, here's an energy diagram for hydrogen. Orbitals in a given sublevel are equal in energy to each other, and in hydrogen's case are also equal in energy to all of the other orbitals in the energy level. Orbitals of equal energy are called degenerate orbitals. The principal quantum number is equal to the number of orbital shapes or sublevels. Squaring this number will yield the number of orbitals. We haven't talked about this yet, but in fact each orbital can hold a maximum number of 2 electrons. This means that 2 times the principal quantum number squared yields the maximum number of electrons that can occupy an energy level. The 3 quantum numbers taken together will always specify a particular atomic orbital, since they tell us its size, shape, and orientation in space. To specify an electron, however, we need to use all 4 numbers, which was a rule proposed by Austrian physicist Wolfgang Pauli in 1925. If 2 electrons are in the same atomic orbital, they therefore have the same first 3 quantum numbers, but because they must have opposite spins, their 4th quantum numbers are different. In hydrogen, all of the sublevels in any energy level have identical energies. For multi-electron atoms, we need to consider the effect of electron-electron repulsions on the relative energies of the sublevels. Repulsive forces cause a sublevel with a greater number of orbitals to have a greater energy. In other words, the order of sublevel energies is S, P, D, F. We can also see that in several cases, energies get closer as the principal quantum number increases. In these cases, repulsive forces are such that some sublevels containing smaller orbitals actually have higher energies than some larger orbitals. For instance, we can see that the 3D level is actually greater in energy than the 4s level. There's another rule associated with describing electrons that we need to be mindful of, the Aufbau principle. This states that when filling orbitals, the lowest energy orbitals available are always filled first. The name isn't that of a scientist, rather it's a German word meaning a building or construction. The principle was in fact formulated by Niels Bohr and Wolfgang Pauli. The order for filling up the orbitals was essentially what was shown in the previous animation. To illustrate how to put this into use, we'll dive straight into some examples. We'll write the full electron configuration and draw the orbital diagram for atoms in their ground state. Let's start with hydrogen, recalling that in its lowest energy or ground state, its one electron exists in the 1s orbital. An electron configuration is a shorthand way of writing this out. This is simply 1s1 for hydrogen, the 1 being the energy level, s being the type of sublevel, and the 1 superscript representing the 1 electron. The other way to represent this is by constructing an orbital diagram which depicts electrons and their spins. One way to draw these is with boxes representing the orbitals and up and down arrows to represent the electrons and their spin. Another, perhaps more efficient way to draw them is using circles and diagonal lines instead. The next element, helium, has a 1s2 configuration. From the Pauli exclusion principle, the orbital diagram shows 2 electrons with opposite spins occupying the 1s orbital. We then have lithium, which has 3 electrons. From the Aufbau principle, this third electron will be in the 2s sublevel and not the 2p sublevel, since the 2s sublevel is lower in energy. To indicate increasing sublevel energy, the boxes or circles can be written vertically or also left to right. If we were to keep doing this for the next elements, we'd reach an issue by the time we got to carbon. Carbon has 6 electrons, and placing the first 5 is relatively easy. But where does the 6th one go? In the same orbital as the 5th electron or a different one? If in different orbitals, do they have the same or different spins? Does it even matter? In fact, it does matter, as stated by Hund's rule, which was formulated by German physicist Friedrich Hund. When orbitals of equal energy are being filled, the most stable configuration is the one with the maximum number of unpaired electrons with the same spin. So, to answer our question, the 6th electron should go here with the same spin as the 5th one. Just for reference, here's what this would look like with boxes and arrows. Now we can apply this rule to nitrogen as well, and as we add more electrons, we can start pairing them off, as we can see for fluorine. You may have noticed the previous question specified that the electron configuration needed to be the full version. This is because there's actually a condensed form of electron configuration known as core or kernel notation. In core notation, the configuration of the previous noble gas is represented by that noble gas symbol in square brackets. We'll illustrate this by looking at scandium and argon. Seeing where the element is on the periodic table can be quite helpful for figuring out the orbitals. For scandium, we know that the first and second energy levels are completely filled, along with the s and p sublevels of the third energy level. Scandium should have 21 electrons in total, and if we sum the superscripts, we indeed get 21. Diagrams such as this may also be helpful when filling up the orbitals, but you need to remember how many electrons each sublevel can hold. Although the 3D sublevel fills after the 4s sublevel, the 3D sublevel still contains electrons that spend most of their time nearer the nucleus, and so is inside the 4s sublevel. Some periodic tables indicate the electron configuration in order of sublevel size, and so will show scandium with 3d1 immediately before 4s2. The previous noble gas was argon, so the core notation would be this, where everything up to right before the 4s orbital can be summarized as just the electron configuration of argon, and the outer electrons are still written out in detail. Now, if we were to do the core notation of argon, the previous noble gas is neon, so its core notation would be this. Although it wasn't part of the question, here are the orbital diagrams for each atom for reference. Our final example will cover the cases of ions. For instance, when writing the electronic configuration for the sulfur 2- anion, we could start out by writing the electronic configuration for sulfur, which has 16 electrons. Then we just need to add 2 more electrons to this last unfilled sublevel. Notice that the sulfide anion now has the same electron configuration as the nearest noble gas, argon. It is therefore considered to be isoelectronic with argon since the two species have the same number and configuration of electrons. To write cation configurations, electrons are always removed from the outermost orbitals with the highest energy first. It is sometimes worthwhile to first write the neutral atom's configuration in core notation, with the final orbitals listed from smallest to largest, rather than in the order the orbitals fill. For the indium-3 cation, we can first write the core notation for a neutral indium atom, but with the sublevels ordered from smallest to largest, which has the d orbitals first. Now, we remove the three outermost electrons to give the core notation for the indium-3 cation. This helps us not make the error of removing the 4d electrons rather than the 5s ones. Note that an indium-1 cation would form by losing the 5p electron, as it's at a higher energy than the 5s electrons. As a final note, there are several exceptions to the orbital filling order discussed here, with two of the most commonly encountered being chromium and copper. In these cases, a completely full or half-full d sublevel is more stable than a partially filled d sublevel. This results in an electron from the 4s orbital being excited to a 3d orbital. Other exceptions include molybdenum, silver, and gold. While this is certainly interesting, writing the electronic configurations of elements that are exceptions to the Aufbau principle is not required on the AP Chemistry exam.